Hey everyone, most of you know me as Q. My name is Quentin Walters and I'm here to present to you about my personal project from the past year called Down Detector. During this presentation, we'll go over who I am, what the competition architect position is, how I recognize the problem, the initial design phase for my solution, its deployment during the RITSEC CTF of 2019, refactoring it into Python, what I did wrong, the lessons I learned, and my future development goals. So who am I? I am a soon-to-be part-time graduate student in CSEC at RIT. I'm an avid reader and D&D player. I prefer to read sci-fi and fantasy, but I'll read pretty much anything. I am a retired competition architect from RITSEC, a USB enthusiast. I've written some difficult CTF challenges that implement the USB standard that I know quite a few club members are a little salty about. And I'm a dedicated learner. I'm currently teaching myself Go. So the competition architect position is an elected position in RITSEC that designs and oversees 2 of the 4 competitions that RITSEC runs. They must manage a development team called the Black Team, and they're the developer of last resort. If something needs to get done, but no one is able to do it, the competition architect has to design it. And it requires a large knowledge base to properly perform the duties. As a competition architect, I was responsible for the incident response security competition and the capture the flag competition. At the CTF, we had over 900 participants from around the world. My job was not only to manage them and their questions, but also the technical portion of the competition. Juggling these 2 responsibilities was where the problem lies. So during the capture the flag competition, there are 2 primary types of challenges, hosted and non-hosted. Non-hosted challenges are downloadable files or strings presented through the CTFD dashboard. And the hosted challenges are live challenges that are publicly available and must be accessible to solve. The problem I noticed was with the hosted challenges. In order for these challenges to be solved, the hosted component must be up and working at all times. To ensure this, the competition architect or challenge authors have to verify if a challenge is broken, and then they have to redeploy the challenge if it is. The main methods to do this are to wait for competitors to either start complaining about the down challenges, verify them, and then redeploy them, or frequently verify the challenges and redeploy as necessary. Both of these methods require constant monitoring of either the competition chat or the challenges themselves by volunteers who are capable of fixing the broken challenges. In the past years, this has led to a profound lack of sleep for the competition architect and the volunteers involved, along with a substantial amount of challenge downtime. Volunteers would sometimes stay up for the entire competition, 60 hours straight. I personally only slept for 8 hours during the 72-hour period that the competition ran, though this was because I was worried that Down Detector wouldn't work, something I didn't actually end up needing to worry about at all. The solution to this problem is the oft-used buzzword, automation. By automating the detection and redeployment of down challenges, the response time improves rapidly, and volunteers are able to get their well-deserved rest. So during the RITSEC CTF of 2019, the first attempt at solving this problem was born, downdetector.sh. It was 219 lines of bash script that was written in the 48-hour period starting 2 hours before the competition. It started only 2 hours before the competition due to delays from challenge authors turning in challenges. The script called 2 JavaScript exploits, 2 Python exploits, and 1 exploit written in C on top of many written in bash itself. For redeployment, it would SSH into the machines hosting the down challenge and restart the Docker containers. Partway through the CTF, our only competition-wide downtime occurred. The city of Rochester lost power for a brief second. However, that was long enough for our entire infrastructure to crash. Half of the virtual machines booted back up cleanly, thankfully. The cron job running Down Detector checked those challenges and brought that half back up before we even had responded to the power outage. The other half were on corrupted nodes and they needed to be manually migrated to working nodes, then brought online. This occurred on a roughly 5-minute interval, the same interval that Down Detector was running checks. I would SSH into the machines as they were being brought up with the intention of restarting the Docker images myself. Down detector, however, would check the challenges, find that they were down, and SSH into the machine I was working while I was doing that. It would then kick me out of the machine, kill the progress I had made with Docker, rebuild the images, and restart the containers without me. It did this for all of our corrupted challenges. Down detector turned what could have been a several-hour down period into less than 45 minutes of downtime. In the past, the club's downtime average was over 2 hours for this competition, and that was without power outages bringing down the entire infrastructure. This brought me to a very big new problem. It wasn't reusable. Because of how I had designed and written it, it was very designed specifically for this competition, and to implement it for a new competition, I had to completely rewrite it. So I refactored it in Python. The goal of this refactor was to increase reusability, to add multithreading, make it platform agnostic, increase the ease of use for both the competition architect and for competitors, and to add a basic web front end. Here we have the basic downdetector.sh execution flow. When it was run, it would check the first challenge. If it was up, it would move on to the next challenge. If it was down, it would log that the challenge was down, redeploy the challenge, and then log that it redeployed. Then it would move on to the next challenge. It would continue in a linear fashion through all the challenges until all of them are checked. If the competition architect or a volunteer wanted to check a specific challenge, they have to comment out the calls to all of the other challenges. This would create some problems if you didn't copy the script and edit the copied one, and you didn't comment or you didn't remove your comments fast enough. Down detector could make a check that had those challenges commented out, and as a result, not check some of the challenges. Here's a simplified execution path of the refactored down detector. This does not include the paths for TAC H, TAC V, or TAC F. TAC H will output the help prompt. TAC V will turn on verbose mode and display all of the logging in the terminal. And TAC F allows you to change what file you're logging to. During this execution path, if the TAC L is present when down detector is run, it will list the implemented challenges and then terminate. If the TAC T flag is present, it will go through the specified challenges after the TAC T flag, and it will execute the solve function for that challenge and log the status for it, update the database that the web server uses, and then if the challenge is up, it will move on. If there's any challenges remaining, it will loop again or terminate. If the challenge was down, however, it will execute the redeployment function and log that it executed that. It will then verify the redeployment using the solve function and then log the status of that solve function, update the database again, and then go back into the loop. If there was no TAC T flag or TAC L flag present, it will then create threads and allocate them out, and then loop through the challenges, assigning them to the threads. During this loop, it'll perform in a very similar manner to the TAC T flag. It will execute the solve function for a given challenge and log the status. It will update the database for that challenge. Then if the challenge is up, it'll loop back around or terminate the thread. If the challenge is down, it will execute the redeployment function and log the status. It will verify the redeployment was solved, log the status of that, update the database, and then either loop or terminate. With my goals for usability, I implemented Python classes. Here you can see the abstract class challenge. This has to be implemented for all of the challenges. In the init, the competition architect or challenge author will place any variables that could change between implementations. Then they have to implement the solve function. This function actually solves the challenge, checking each step to make sure that it is not down or vandalized. This must return false at the first time it encounters a break in the challenge or vandalization. And then the redeployment function will be where the competition architect implements their redeploying functionality. For my implementations that I tested, I used Paramiko to SSH into another Ubuntu VM. and then I would use Python to drop commands directly into the shell to kill the current Docker image, rebuild the image, and start a new container off of it. With this implementation, adding or removing a challenge is very simple. You just need to add a implementation of this abstract class, which is more or less copy pasting the class and adding your custom code to it. For multi-threading, while Python doesn't actually have true multi-threading, I implemented pool from the multiprocessing library for the closest approximation. I did this to increase the speed of checks and to decrease the chance of checks colliding. With the bash version of Down Detector, I ran into problems near the end of the competition. Because it took so long to run through all of the checks, it would start colliding with the execution of the next check. This caused some problems with there being a lot of time between when you get the previous check and the next check for a challenge. And I wanted to reduce that amount of time as much as possible. And multi-threading allows you to kind of take advantage of modern systems and architecture. If you have a beefy VM that Down Detector is running in, you can allocate more processes to it and it will run faster. If you have a weaker VM that's running it or for physical host, you can dial back the number of threads so that you don't bog down your machine. The Python logger, however, will rapidly be filled with logs from the multi-threading library. To remove this noise and ensure that only the messages I wanted were captured, I used a logging object with the debug level, and then I attached standard out and a file handler depending on the command line arguments. The second issue caused by multi-threading was that if the main process terminates before any of the child processes, any logs from those now orphan child processes will be lost. They won't be logged to standard out, they won't be logged to the actual logger, and they won't hit the log file. To solve this, I use pool's apply function, which blocks the main process until child processes are completed. Now, when you run it, any of the child processes will finish out before the logger is killed. So if you're running in verbose mode, it'll actually get written to your terminal and your logs will actually be written to your logging file. It won't just kill out and you'll be wondering, why am I not getting any logs? One of my other goals for the refactor was to make it platform agnostic. Bash can only be written on or only be run on machines that have the bash shell on it. So it's kind of hard to do that with Windows, and it gets a little finicky with other specialized OSs. However, Python can be installed on many different OSs. It's as long as Python's compiled for it, you can drop it on it and you can run Down Detector. Docker containers also don't require a specific OS to run, as long as Docker is compiled for it and supports that OS. You can run Down Detector on it. The IIS or Nginx or SQL images that are used don't require a base OS of a specific form. So yes, Dan, you could theoretically run Down Detector on React OS, so long as you have either Python compiled for React OS or Docker compiled for it, and you write your solve and redeployment functions to support it. If you're running your challenges on a Windows machine, you could write your solve and redeployment scripts to support Windows using PS Remote or PS Exec to connect to that machine to restart however you are running that challenge. I wanted it to be easy to implement Down Detector for a competition. Using Python classes, it's practically copy and paste to integrate challenges. This means the barrier for entry is really low. Competition architects can use Down Detector without any special training on it, and hopefully this will lead to other groups using it when they run CTFs. The command line arguments further simplify the implementation. Instead of editing a config file or the code directly, the competition architecture volunteers can easily modify the tooling to fit their needs. If they want to check a single challenge quickly, they can run Down Detector with the TAC-T and TAC-V flags to target a specific challenge or group of challenges and see the output in their terminal without having to check the log file. In the bash version, if you wanted to check a specific challenge, you had to comment out all the other challenges. And then once you run it, you have to check the log file to see how it worked. It didn't output to the terminal. The TAC-P flag sets the amount of processes to use, so the CA can fully take advantage of their infrastructure. And if their infrastructure isn't able to run a multi-threaded process, they can dial it back and only run one process on it so that they don't burn out their infrastructure or cause any problems. They can also use the TAC-F flag to specify which log file they want to use. It defaults to downdetector.log, but if you want to run your on-the-spot checks using a different log file, or if you just for some reason didn't like the downdetector.log file, you can specify a different one. So it makes it a lot easier to customize. The original form of down detector required the competition architect or a volunteer to notify competitors when a challenge was down. And it also required volunteers to ask us if a challenge was down. I wanted to streamline this process, and to help reduce the amount of messages that overwhelm the CA, I personally was getting upwards of 10 messages per second at points in the competition, which is a tad overwhelming. And sometimes a lot of it was, hey, is this challenge down? Is this challenge down? Is this challenge down? And I had to tell them, no, it's not actually down. You're just doing it wrong. For this web front end, I use a simple database setup that I learned about during Heim's web class. The script updates the challenges within the database every time it's run. This sets the current status of a challenge, when it was last checked, and the last time that it was up. When a user accesses the web server, it queries the database for the information and returns it in a simple HTML table. For security reasons, the competition architect will have to ensure that the database port is not accessible externally and that only the web server port is. This unfortunately adds a layer of complexity to the setup process that I want to streamline down the road. This method is also susceptible to denial of service and distributed denial of service attacks because I have not yet put a query limit in the web server. This is a failing on my end and something that I will keep in mind as I add more features to the web server and something that I want to fix in the future. It's also a very bare bones implementation. As you can see here, this is the output when you visit the down detector site. It just tells you, it gives you a nice big table with the challenge, what category that challenge is in, its current status, when it was last checked, and when it was last up. It's not very pretty, it's not very user readable, but it works. So what I did wrong during this project. My initial design was very rushed, and as a result, it was effectively just the solve and redeployment scripts stacked on top of each other. This was very haphazard, and it stacked problem after problem. To convert it properly to something reusable, I had to go back to the drawing board. After extensive redesign, I ended up with a solution that can be improved upon when features are suggested, and it can be easily deployed in a variety of environments. As I just mentioned, my initial design was rushed and haphazard. Without a secure design foundation, was not something that would last. As it got larger and it got harder and harder to work with, part of this can be attributed to my lack of knowledge when it comes to bash practices, and the rest comes down to poor initial software design. I had experience writing short bash scripts and one-liners, but I didn't really have experience with writing a larger program. I neglected to look up the best practices for it, and as a result, my code could not really be read by another person, and I could barely understand it after I got some rest. In the end, I would rather develop large programs in Python over Bash. I found it easier to deal with, and I'm more familiar with it. My last major mistake was to continue development beyond the 36-hour mark without sleep. The longer I went without a proper rest, the worse my code got. I accidentally introduced bugs into my code while I was extremely sleep deprived that I only noticed after taking a short nap. If I had taken time to rest while Down Detector oversaw the challenges, I would have wasted less time on fixing my bugs and poor design choices. Shannon, do you mean the presentation or Down Detector? So when I first started working on it, I probably had about 6 hours of sleep. because I didn't sleep well the night before the CTF because of how stressed I was. I then continued it and did about 36 hours without sleep for the first night. Got about 2.5, 3 hours of sleep in the hammock in the sky bridge. Then I started working on it again. And yeah, it didn't go well. Whoops. So some lessons learned. As I mentioned in my last slide, during my initial development, I did not spend enough time on the design process. When I refactored it into Python, I made sure to give myself several days to design, a lot of scratch paper to map it out, and then I finally began to code. When I decided to add the web front end, I did the same process, a lengthy design period with scratch paper to ensure my logic was sound, then finally working on a new branch. Finally, my introduction to object-oriented programming in Python was with a custom class interface called RITLib. It was overly complicated and made interfacing with objects a pain, to say the least. Micah Martin told me to look into object-oriented programming in Python, specifically in Python classes. After some research, I found it is much easier than my past experience and made the project being much more fun to develop and made it a lot easier to implement. Shannon, yes, the GUI will be public for competitors to view. All it takes is the competition architect to add a Nginx forward into the Nginx front end on the CTF so that they can access the front end, but it is intended to be visible to the competitors. Future web display, I want to implement a Jeopardy style board so competitors can quickly find the information they need. I want to add a check request button so competitors can request a challenge to be verified without messaging the moderators and have it automatically check that challenge. And I want to add notifications for when a challenge is down so the CA or volunteers can get some sleep soundly, knowing that if something goes down, their phone will wake them up because Down Detector messaged them. And there we go. The GitHub repo is Down Detector on my GitHub. Thank you all.